Hello, today I would like to show you what I think is very interesting geometric visualization of Pascal's triangle, or the binomial coefficients. I'm going to assume that you already know something about Pascal's triangle. You know that the numbers in Pascal's triangle represent um, the, all the possible combinations of selecting n objects out of m total objects. For example, in the fifth row of Pascal's triangle, if we count this one as the 0th row, we have got the ways of selecting n objects out of 5 total objects. For example, there's only going to be one way of not selecting any of the objects. There is going to be one way of selecting all 5 of the objects. There are going to be 5 ways of selecting one of the objects, because I could select any one of the 5. There are also 5 ways of selecting 4 of them, because I could leave out any one of the 5. There's going to be 10 ways of selecting 2 objects. That takes a little bit more thought. Also 10 ways of selecting 3, because there's going to be 10 ways of leaving out 2 of them. And in general, these binomial coefficients can be written as m choose n can be written as m factorial divided by n factorial times m minus n factorial. It's very simple, very beautiful. So much that we could say about its uses in probability and combinatorics. We want to look at a particular application here, though. I think it's also very interesting, for example, to look along the diagonals of Pascal's triangle this way. And I'm going to call these the columns, okay, because we could actually set this up as a right triangle. We could set Pascal's triangle up as a right triangle and make these columns. So I'm going to call these the columns. And as I look at the columns of Pascal's triangle, which of course are symmetrical both directions, the first column obviously is all 1. But there is a summation going on here called the hockey stick identity, which if I want to know any number in a diagonal, I can add up all the ones in the previous column to that point. So for example, 1 plus 1 plus 1 plus 1 equals 5. Add another 1, I've got 6. Add another 1, I've got 7. And that's how I get the counting numbers in the second column, because I'm adding up successive ones. If I add up successive counting numbers, I've got the famous sequence 1, 3, 6, 10, 15, 21, 28, which is called the triangular numbers. And we can visualize these like this, where we are adding the different rows represent the successive counting numbers that I am adding. So here are the first 6 triangular numbers. If I go and I take a look at what happens when I add up the successive triangular numbers, I'm going to get, 1 plus 3 is 4, 1 plus 3 plus 6 is 10. I am going to get this number sequence, which I could think of as the tetrahedral numbers. And I could visualize it this way. Right? The different rows or layers of the tetrahedron represent the successive triangular numbers that I'm adding one at a time. 1, 1 plus 3, 1 plus 3 plus 6, 1 plus 3 plus 6 was 10, etc. Now it makes sense that if I add up the successive tetrahedral numbers, I am going to get the 4-dimensional equivalent of a tetrahedron, which has several names. I'm going to call it the 4-simplex. We could also call it the pentachoron. It has other names. But in fact, we do. We get basically a 4-dimensional tetrahedron, 5-dimensional, 6-dimensional, etc. So I like to think of these number sequences as what I call the triangular powers. And they are a lot like the regular powers, n, n squared, n cubed, n to the 4th power, etc., but with some obvious differences. These triangular powers have pretty cool formulas. And the formulas that I'm going to give here is assuming that I am starting up here at the 0th row each time. So I'm going to have some extra zeros. They're going to be offset a little bit. And we can see the formulas right here. The first column, these are just always 1. The second column are the counting numbers n that has a 0 at 0, right? That's a 0 at 0. These are the triangular numbers offset by 1, n times n minus 1 over 2. And this function has zeros at 0 and 1. right? We have zeros at 0 and 1. This is the tetrahedral numbers, and this has zeros at 0, 1, and 2. And then we've got the four-dimensional numbers, n times m, four-dimensional triangles. And we've got this beautiful pattern in the sequences that continues. There's another way to see Pascal's triangle in these multidimensional triangles, which are called the n-simplexes, on this infinite family of polytopes. And that is to look at the number of elements of each dimension in each one of them. So the simplest simplex is just a simple point, and that has just one element of dimension 0. The next simplex is a simple line segment, and this has two elements of dimension 0 and one element of dimension 1. A triangle, of course, has 3 points, 3 elements of dimension 0, 3 line segments, 3 elements of dimension 1, 1 plane, 1 triangle, 1 element of dimension 2. My next simplex, the 3 simplex, is of course the regular tetrahedron, and 4 points, 6 line segments, 4 planes, 1 solid. Okay. To visualize the pentachoron, the 4 simplex, you can put a point at the center of a tetrahedron and connect it, and imagine that you've got one outside tetrahedron and then one tetrahedron going in on each face. And if we imagine that in 4 dimensions, it's possible for all 5 of these tetrahedra to be the same shape and size. We've got a little bit of a visualization of this pentachoron or 4 simplex. And you see we've got 5 points, 10 line segments, 10 triangles, 5 tetrahedra, and 1 4-dimensional polytope. Okay, and we could continue there, and you can see that you've got all the numbers in Pascal's triangle except for the first column. There is another way to visualize this two-dimensionally, and that's what I want to show you now. It is basically looking at all the ways to connect n points, or m points, since we're doing m choose n. For example, if I only have 2 points, there is only one line segment I can draw between them. If I have 3 points, I can draw 3 line segments, and that is 3 choose 2, because each line segment represents one way of choosing 2 of the 3 points. If I have 4 points, I've got 4 choose 2, or 6 possible line segments. And if I keep going, 5 points, 10 line segments, 6 points, 15 line segments. Another way to think about that, when I starts to get hard to count here, is that each of my 6 points connects to 5 other points, but each of those line segments will be counted twice because A to B is the same as B to A. So divide by 2 to eliminate duplicates. 6 times 5 divided by 2 is 15. That's n times n minus 1 over 2. And I can do the same thing with more points, right? Each of my 7 points is connecting to 6 other points. Eliminating duplicates, that's 21. That's 7 choose 2. With 8 points, I've got 28 possible line segments. And you can see that we've got the triangular numbers here. And in the past, I've used this pattern to introduce number sequences, and the triangular numbers in particular, to my students. But I never really thought about what would happen if we looked at the other shapes within these patterns. For example, this square is really a perspective version of a tetrahedron. It's just viewing a tetrahedron with the edge on top. I don't know if you can see that here. I've tried to draw that a couple of different ways. But you've got 2 triangles on top here, and then 2 pink triangles that are hidden from view. And so if you think about it, I have got 4 points, 4 vertices, my 6 edges, my 4 faces, and my 1 solid. And now it also makes sense what this number is in the first column of Pascal's triangle, because there is only one way to select 0 points, but there are 4 ways to have 1 point, 6 ways to select 2 points, 4 ways to select 3 points, those are my triangles, and 1 square, one way to select all 4 points. Now, I wanted to think about what would happen if we did this with more than 4 points. So let's take a look at what this would look like for a regular pentagon. All right. Now, obviously, if I don't select any of the points, there's only one way to do it. If I select all 5 of the points, I've got a pentagon. There's only one pentagon that I can draw. If I select one of the points, I could select each of the 5, and that's what I've got in green here. So going around selecting each of the 5 points. But if I look at what the other 4 points make, they make a quadrilateral. Right? So if I like what I have left, I've got this trapezoid, and this trapezoid is also going to go around, so I can see I've got 5 trapezoids. So not only do I have 5 possible points, but I've also got 5 possible quadrilaterals that I could draw inside my regular pentagon. And I drew these diagonals in to show a couple different things. One, to show the way that you could build each of these trapezoids out of 2 triangles, but also to give a little perspective and show that each of these quadrilaterals is really a tetrahedron. And so what I've got here, when I've got this famous pentagram here, is I've got a 2D perspective of a 4-dimensional triangle, a 4-simplex. Yes, it looks quite a bit different than the perspective 4-simplex that I drew here, but it's connected in exactly the same way. And like this one, it is made out of 5 tetrahedra, and I just showed what those 5 tetrahedra are. They are my 5 trapezoids. But from now on, I'm basically going to think of this all in 2 dimensions as polygons. So I've got 5 points and 5 quadrilaterals. The other way to split the points would be in 2 and 3. When I split, when I take out 2 points, obviously there are 10 line segments, 10 ways that I could do this. And for each of these 10 line segments, when I connect the points that are left, I am going to have a triangle. So here are my 5 edge segments and my 5 edge triangles. And these isosceles triangles I'm going to call my 1, 1, phi triangles, because if the side length of my regular pentagon is 1, the diagonal will be phi, approximately 1.618. The other thing I could do is I could select one of my diagonals, and there's 5 ways to do that, and I've got 5 more, another family of 5 isosceles triangles. I can call these the phi phi 1 triangles from their lengths. So you can see I've got 10 line segments in my pentagon and 10 triangles, right? One way to select 0 points, 5 points, 10 line segments, 10 triangles, 5 quadrilaterals, and 1 pentagon. Let's take a look at what this looks like with hexagons. All right, obviously, there's only one way to select none of the points, and there's only one regular hexagon. But if I take out 1 point, I could take out any one of the 6, so there are 6 points. If I look at what I have left, the remaining 5 points connect to make an irregular pentagon, but it still connects in the same way. I could draw a subset of the diagonals, and I've got this pentagram hidden inside my hexagon. All right, and this, of course, represents, now I've got a 6-simplex, and these represent the 6 5-simplexes hidden inside of it. All right, so 6 points, 6 pentagons. If I take out 2 points, there are 15 possible line segments, right? 6 choose 2. I had 15 line segments here. These line segments are going to go in families, and let's take a look at them. Okay, if I look at the 3 center diagonals of a pentagon, what I have left is 3 rectangles. if I take a look at the 6 edge segments, the remaining, what I'm going to have left is 6 trapezoids. If I look at the 6 segments that make the Star of David, I am going to have 6 kites that correspond to those. So I've got 15 segments and 15 quadrilaterals. And I can classify these segments as my segments of length 1, my segments of length 2, and my segments of length square root of 3, using the geometry of a regular hexagon. All right. And I could draw the diagonals of these quadrilaterals to show them built up from triangles, also to show them as perspective tetrahedra. Okay, the other way to split these points instead of 4 and 2 would be 3 and 3. So I can split them into triangles. If I take out a triangle, I'm going to have a triangle. All right, so far I have got 15 line segments and 15 quadrilaterals. I'm going to expect 20 triangles, and here's where they come from. If I look at my smallest isosceles triangle, I'm going to call these the 1, 1, square root of 3 triangles, or the 30, 30, 120 triangles. I've got 6 of these because the point could be at any one of the 6 points of the hexagon, and here are my 6 of these triangle. Okay. Obviously, I've also got 2 equilateral triangles, 60, 60, 60, square root of 3, square root of 3, square root of 3 for side lengths. I've got these 2 equilateral triangles, and that makes my Star of David, so that's 2 more triangles. Now I have got 12 right triangles. These are all scaling. They come in left and right-handed versions. For example, if I pick the bottom segment, I can have a left-handed one or a right-handed one. That's why I've got 12 total instead of 6. And these are my 30, 60, 90 right triangles, or 1, 2, square root of 3 as my side lengths. So very beautiful here. I've got 12 right triangles, 12 scaling triangles, 6 isosceles triangles, 2 equilateral triangles for a total of 20 triangles. All right, I also just showed how we could look at these, for example, the kites split up into triangles in different ways. Next, let's take a look at heptagons. Obviously, I've got only one way to select 0 points. I've got only one heptagon, but I've got 7 points and 7 hexagons created by taking out one of the points of the heptagon. Here I drew in all the diagonals. You can see the Star of David. It's been bent and distorted here, but this is my 6 simplex hiding inside my 7 simplex, and there are going to be 7 of those. And I just showed some different ways that this could be split into triangles just for fun. And here are some more ways. And there are at least a couple others that I didn't have room to draw. Now, if I take out 2 points, that is the number of line segments here, I am going to have 21 possible line segments. So I'm going to have 21 possible pentagons, and they're going to come in 3 types because I've got 3 different line segments. I've got this line segment, edge segment, I've got the one skipping 1 vertex, and I've got one skipping 2 vertices. Right? So here's my 3 lengths. I'm not going to calculate those. Those are kind of odd because it is a heptagon. 3 different lengths of segment, and each of these segment types has a pentagon type that goes with it, and they're all symmetrical. The polygons formed by n minus 2 points are always going to be symmetrical because the segments always have twofold symmetry, so we're going to have twofold symmetry for our n minus 2 polygons. Here for our pentagons. So we've got 3 different types of pentagons. I wanted to show the pentagram inside of each one. I wanted to show several ways that they could be split up into triangles. So take a look at that. Okay. All right, so you see here that we have got 21 possible line segments and 21 possible pentagons. The other way to split this up is going to be into 3 and 4 triangles and quadrilaterals. And I'm going to have 35 of each by Pascal's triangle. And this is how they are split up. So I've got 7 of these little isosceles triangles and 7 of these little trapezoids matching them, 1 at each point of the heptagon. 7 of these bigger isosceles triangles and 7 bigger trapezoids here. 7 long skinny isosceles triangles and also 7 more matching trapezoids. My other possible triangles are scaling, and they come in left and right-handed versions. So at each segment I could have a left-handed version or a right-handed version. So I've got 7 and 7 and 14 of these and 14 matching trapezia, odd-shaped sort of ice cream cone, not quite a kite. I'm going to call them pseudo-kites here, left-handed and right-handed ones. So you see I've got 7, 7, 7, 7, 7, or 35 triangles and matching 35 quadrilaterals. And I just showed that some of the ways that these could be split into triangles, that they could be viewed as perspective tetrahedra. So I've completed my picture with 7 points, 21 line segments, 35 triangles, 35 quadrilaterals, 21 pentagons, 7 hexagons, and 1 heptagon. The last one we're going to take a look at is an octagon. And obviously with an octagon we've got 28 possible line segments. This is my 8 simplex or 8-dimensional triangle. And when we take a look at this here, let's first, obviously we've got only one octagon. We've got 7 heptagons because we've got 8 heptagons because we've got 8 possible points that we could leave out. So 8 points, 8 heptagons. If we take out 2 points, we're going to have 28 possible segments and 28 possible hexagons. And they are going to be in 4 different families because I have 4 different edge lengths here. I've got the smallest edge length, and then diagonal 2, diagonal 3, and then the center diagonal or the longest diagonal right here. They're not all quite created equal here because there are only 4 center diagonals. So there are only 4 of this type of hexagon, a little bit more symmetrical. It's got 2 lines of symmetry. And I've got, since any of these could be at 8 possible positions, I've got 8 of these and 8 of these hexagons, 8 of these, 8 of these hexagons, 8 of these, 8 of these hexagons. That makes 28 hexagons and 28 segments. Next, we could split them into 3 and 5. That's going to be triangles and pentagons, and we're going to expect 56 triangles and 56 pentagons, and they are broken up into several families. And let's look at those families here. So I've got 8 of my smallest isosceles triangle and 8 of this gambrel roof, barn roof, pentagon that goes with it. I have got 8 of this next largest isosceles triangle. This is half of a square, and 8 of this house-shaped pentagon that goes with it. I've got 8 of this particularly pleasing looking isosceles triangle and 8 matching ones of this almost perfect pentagon that matches it. The other 2 families come in left and right-handed versions because they go with scaling triangles. I've got these right triangles and the matching shed roofs here, or sheds, pentagons, and I've got 8 left-handed ones and 8 right-handed ones for a total of 16 triangles here and 16 pentagons. And then I've got this odd-shaped triangle, 8 and 8, and this odd-shaped pentagon, 8 of these and 8 of these. So all in all, I have got 8 times 7 families, or 56 pentagons and 56 triangles. Okay. Last, we're going to split these into 4 and 4, and we're going to expect 70 quadrilaterals. And here they are in several families. The simplest one here, obviously, is going to be squares. And there are 2 possible squares. They make an interlocking star, 8-pointed star here. two squares, there are four rectangles, two this way, two that way. Then I have got a bunch of trapezoids. First, I've got 8 of these trapezoids. So you see I've got this rectangle in the middle. I've got 4 of those rectangles, so I've got 4 times 2, or 8 of these trapezoids. Similarly, I could turn this along the 4 main axes, the 4 main diagonals here, and I have got 8 of these larger trapezoids coming in pairs of 2. Notice that this duality here creates identical shapes. So identical trapezoids here, identical trapezoids here. We have an exception here where we've got this trapezoid, the dual is a kite, and I've got 8 of those kites. The point could be at any of my 8 points, and 8 of these matching trapezoids, and I've drawn ones facing a couple different directions to kind of complete that picture. You can think of these ones up here as coming in left and right-handed versions, and I've got 8 left-handed versions and 8 right-handed versions for a total of 16 of these, right? Because this configuration has a line of symmetry right here, and that could be at any of the 8 points of your octagon. And all in all, then, I've got 8, 8, 8, 8, 8, 8, 8, 8. That's 64, 66, 68, 70 quadrilaterals here. So that kind of concludes our tour up to an octagon of visualizing binomial coefficients as convex polygons, right? So this is 4 choose 4, or 8 choose 4, which is 70. For example, and I hope that you enjoyed this little tour and that it'll spark some of your own thoughts and researches. Obviously, we have just dived in to the very beginning of what you could do with these. We could do a whole lot more. And I hope that you add your own thoughts about the different directions that you could take the math here. Thanks. I look forward to talking to you again.